then stopped. That's not good. I think we're back. I don't know why the movie recording would have stopped. I hope I didn't run out of batteries because we still have a ways to go. Alright, so going to go ahead and move that and get on with our next couple reactions. So this will go to a safe place for cleanup. Next we have one of my favorite demos, which that is just a beaker full of water. To that beaker with the water, I'm going to add an indicator. This indicator solution will tell us if there are hydroxide ions present in a solution. What will happen is phenolphthalein in a basic solution turns pink, like a bright pink-red color. Then the first thing I want to do is show you what sodium metal looks like. And sodium is highly reactive. It's one of the alkali metals. So it has to be stored in kerosene or something like it, mineral oil, something like that. And you'll notice that it's all kind of rusty and corroded on the outside. But if I slice it, and you look at a freshly sliced piece, and yes, I can slice it even though it's a metal. Looking at a freshly sliced piece, if I can focus on that, you can see that it's got some shine and some luster to it. There you go. But it really doesn't, it will dull up because it reacts with the oxygen in the air very quickly. So if I take a small piece of this sodium metal and put it in the water, you'll be able to observe how reactive sodium is. I think I'm going to turn the light off for this one as well. So we will put the sodium metal into the water. And you can't see it with the light off. Alright, well that's a bit of a bummer. So I'll go turn the light back on. And you can see that the sodium doesn't even sink. And sometimes it'll catch fire, sometimes it won't catch fire. But it produces enough hydrogen gas that it just floats on its own little bed of hydrogen as it's in there. And so you can see what it will do. Oh, that wasn't phenolphthalein, it was thymolphthalein, which turns blue. So I'm going to put the right indicator in this time, but you'll end up seeing that it'll turn pink pretty much immediately with that indicator, and that shows that a hydroxide was formed in that reaction, or at least a basic ion. In this case it is hydroxide. So then, just to emphasize that elements in the same group, same family, the same vertical column on the periodic table have similar properties. I also have some elemental potassium here, but you'll notice that the atomic number of sodium is 11, whereas the atomic number of potassium is 19. And if you compare their electron configurations, both of them end in S1, but because they end in S1 just means they have one valence electron extra to get rid of, and if they get rid of that electron they'll be stable. But potassium has an entire extra layer of electrons. Remember, potassium is 4s1 whereas sodium is 3s1, and that extra layer of electrons shields the nucleus, the positive charge of the nucleus, and it makes it even easier for that one electron to be gotten rid of. And so potassium metal, very similar in its appearance, a soft, shiny metal, but potassium is even more highly reactive than sodium. So here is a chunk of potassium, and you'll notice when I cut it how shiny the surface is. Well, you won't notice if I don't have it on camera how shiny the surface is right after cutting it. So I'll do that again. Nice bright shiny surface where it was cut, but it immediately dulls because of the oxygen in the air reacting with it, along with the water vapor. And so potassium metal is even more highly reactive than sodium. You'll notice that it immediately bursts into flame when put in water. So pretty cool. Alright, so I will put all of these relatively dangerous chemicals back under lock and key here shortly, because there have been incidents where people wanting to do not nice things have gotten a hold of these alkali metals at schools in the past and done things like destroy plumbing and all sorts of other things, and actually even hurt themselves. When you go to clean up this, you can get it on your scupulas and then just put your scupulas in the water, and that way any of those extra things that you don't really want are taken care of. So for the so far we've done reactions 1 and 2 and 3 and 4 and 5 and 6 and 7. Actually, we have not done reaction 2 yet. So reaction 2 is taking the hydrogen gas that was collected in this balloon, and we're going to ignite it, and it should make a boom. So take it off of there, and I will tie the balloon off. One thing that is very noticeable about the hydrogen gas is that it's lighter than air, so the balloon floats, or is at least neutrally buoyant. It's a relatively heavy balloon, and there's not a lot of hydrogen in there, but it was able to collect a little more hydrogen gas, it would float. But of course it's 2020 and I'm filming demos, so there you go. So what we're going to do in order to ignite this, and normally I'd have a lovely assistant or two as students to help me out with this, but in the case of today, I'll just have me, so bear with me here. And because I don't want to be super close to this reaction, I've put it on the end of a meter stick right here, as you can see, and on the other end of another meter stick I have a splint that I'm going to burn, and then I'll put the two of them together on camera and hopefully we'll get a nice explosion. I'm going to turn off the lights for this one. Oh, and the tape came off. Wonderful. So, we're experiencing technical difficulties. Please stand by. All right, well, we're just going to blow it up while it's on the counter.